On the silent plain of Mars, a Chinese rover sent an unexpected signal deep from beneath the surface, evidence of buried, polygonal terrain nearly 65 meters down, somewhere no probe had ever revealed such a pattern before. This data, gathered by Zhurong's ground-penetrating radar, now challenges years of Mars climate models and everything we assumed about water and ice at low latitudes. This is a discovery that forces us to rethink the distribution of subsurface ice and the planet's recent climate history. What exactly did China find, and why does it upend what we thought possible on the red planet? A radargram at first glance looks like a blurred barcode, a series of horizontal lines and shifting bands stretching across the screen, each one representing echoes from deep beneath Mars's surface. In Zhurong's dataset, something stands out. A set of repeating, sharply defined reflectors slice laterally through the noise at depths between 35 and 65 meters. These are not random. They trace geometric patterns, almost polygonal, echoing terrain normally seen at much higher latitudes, but never this close to the equator. Time frequency analysis, a technique that separates overlapping signals by their depth and strength, reveals these bands are not artifacts or instrument glitches. Instead, they persist across multiple scans and rover positions. The lateral continuity of the reflectors, sometimes stretching more than 1 kilometer, suggests a broad, ancient structure buried beneath the regolith. A closer look at the morphology shows the bands dipping gently, with inclinations averaging around 6 to 8 degrees. Their dielectric properties, inferred from signal strength and travel time, point to materials unlike the surrounding basaltic sands, possibly ancient sediments or remnants of ice-rich layers. Independent radar specialists reviewing raw and processed frames confirm that the polygonal pattern is not the result of surface features or shallow layering. Instead, it points to a history of thermal contraction or water-driven processes, frozen in place for billions of years. The radargram, once cryptic, now reads as a record of Martian climate and geology, written in hidden layers below the red dust. Scientists across the globe are paying close attention to what Zhurong's radar has uncovered. The polygonal patterns and dipping layers found at 25 degrees north challenge decades of climate models that predicted permafrost and freeze and thaw cycles only at much higher latitudes on Mars. Until now, evidence of ancient ground ice and periglacial activity was confined to the polar and mid-latitude regions, far from the sun-warmed equatorial plains. What Zhurong has detected forces a reconsideration of how Mars once cycled water, heat, and perhaps even life-sustaining chemistry across its surface. If these buried structures truly formed through thermal contraction or ancient freeze and thaw, it means that Mars's climate once allowed icy processes to reach much farther south than previously thought. This single finding, provisional as it is, hints at a planet with a much more dynamic past, a world where cold and warmth, dryness and moisture collided in unpredictable ways. It calls into question the boundaries that scientists once drew between Mars's frozen poles and its supposedly arid lowlands. Yet the implications are not settled. Researchers are cautious, knowing that radargrams can be deceptive and that alternative explanations, such as ancient floods, volcanic layering, or sedimentary cycles, must be rigorously tested. The latitude of this discovery alone, however, is enough to spark debate. It suggests that Mars's climate history is more complex and perhaps more Earth-like than standard models have allowed. For planetary scientists, the next step is clear. Every hypothesis must now be re-examined in the light of this unexpected evidence. Zhurong's ground-penetrating radar was designed for one purpose: to see what orbiters and cameras could not. Mounted low on the rover's chassis, the radar swept the Martian soil with two independent channels. The low-frequency band, operating between 15 and 95 MHz, could penetrate as deep as 100 meters, mapping broad structures and buried layers. The high-frequency channel, tuned from 450 to 2,150 MHz, focused on the uppermost 10 meters and captured fine details with centimeter-scale resolution. Each radar pulse sent a wave of energy into the ground, bouncing off interfaces where the electrical properties changed: rock to ice to sediment, or sand to ancient clay. To avoid interference and maximize clarity, the rover advanced in precise increments, pausing every 25 centimeters to record a new trace. The raw signals, often distorted by noise and surface clutter, were processed using advanced algorithms, including background subtraction, band pass filtering, and time-frequency analysis. This careful workflow stripped away false echoes, sharpening the image of what lay below. Unlike orbital radars, which blur features across hundreds of meters, Zhurong's radar resolved narrow bands and geometric patterns that would be invisible from above. The instrument's design and methodical sweep made these hidden Martian stories readable for the first time. Every command sent to Zhurong had to cross the gulf between Earth and Mars, with a round-trip delay ranging from 5 to 20 minutes, depending on planetary alignment. The Tianwen-1 orbiter played a critical role as the communications relay, passing instructions from mission control in Beijing to the rover on the surface, then returning data packets for analysis. Each morning, the orbiter swept overhead, establishing a narrow window for uplink and downlink. During these passes, engineers queued sequences of commands, adjusting radar parameters, scheduling imaging runs, or targeting new traverses based on the previous Sol's findings. The workflow demanded precision. A typical cycle began with ground teams reviewing fresh data, identifying anomalies, or promising features in the radargrams, then crafting new instructions for follow-up scans. These commands traveled to the orbiter, which relayed them to Zhurong during its next pass. Once executed, the rover's instruments collected new data sets, which were stored and then transmitted back through the orbiter's high-gain antenna. Within hours, scientists in Beijing and partner labs worldwide could examine the updated results, refining their interpretations and planning the next move. Mission Operations lead Zhang Rongqiao described this process as a relay race across space, where each handoff, Earth to orbiter, orbiter to rover, and back, had to be perfectly timed. The synergy between ground control, orbiter, and rover allowed for rapid response to unexpected findings, turning raw radar traces into actionable science within a single Martian day. Orbital imagers have long shaped our understanding of Mars, but their perspective comes with limits. Instruments like NASA's HiRISE camera, circling hundreds of kilometers above, capture surface details down to a quarter meter per pixel. Yet when it comes to peering beneath the ground, their radar, while powerful, can only resolve features at a vertical scale of 10 meters or more. Subtle boundaries, thin sediment layers, or narrow bands of ice are blurred together, lost in the averaging of signals over broad swaths of terrain. Zhurong's ground-penetrating radar, by contrast, moves just centimeters above the soil. Its dual-frequency design allows for both deep probing and fine-scale imaging, resolving layers and buried structures that orbiters simply can't detect. The difference is not just in depth, but in clarity. While orbital radars like SHARAD have mapped thick ice deposits at the poles, they miss the complex, dipping reflectors now revealed in Utopia Planitia. As one principal investigator for orbital imaging remarked, "From orbit, we see the broad strokes. From the surface, the fine print comes into focus." Zhurong's data fills a crucial observational gap, showing that even well-studied regions can hold secrets invisible from space. This discovery is not a matter of better or worse technology, but of complementary strengths, each perspective adding a new layer to the Martian story. Inside the Beijing Aerospace Control Center, the mood shifted as the implications of Zhurong's discovery became clear. Engineers and scientists, many of whom had spent years preparing for routine soil scans, now found themselves at the center of a debate that stretched beyond technical achievement. The radargrams from Utopia Planitia did not just rewrite a chapter in Martian geology, they forced a reconsideration of what future missions should prioritize. Sample return plans, once focused on the familiar terrain of Jezero Crater or the polar caps, now included proposals to target these newly revealed layers. Teams began drafting payload invitations and reaching out to international partners with a simple message: help us understand what lies beneath these ancient Martian beaches. The rover science lead reflected on the data and said, "We always imagined Utopia as a quiet plain, but the subsurface tells a story of tides, waves, and change, one we never expected to find here." For many on the team, the discovery was more than a scientific surprise. It was a validation of years of careful engineering and international collaboration. The roadmap for Mars exploration, once narrowly defined, now stretched in new directions. The search for life, past or present, will have to include these low-latitude deposits, their secrets buried just out of reach. Each new plan and each collaboration carries the excitement of being part of a story still unfolding. Right now, Mars remains a frontier defined by unanswered questions, and every new signal redraws the boundaries of what we know. As nations race to decode its secrets, the stakes shift from pride to possibility. The search isn't over. Our sense of wonder is just beginning. Share your thoughts below.